Greetings. Today we're gonna talk about advanced trigonometry. So first of all, I'd like to give you a recap, and this is a unit circle in which it shows which ratios are positive in which quadrant. Like first quadrant, all ratios are positive. For second quadrant, sine is positive. Third, tangent is positive, and the fourth, cos is positive. So if you want to know more about the unit circle, just go back to the basic trigonometry video. And now I want to explain something about what can be derived from the unit circle. As such, there is an odd even relationship that's obtained, such that sine negative x will give negative sine x, cos negative x will give cos x, and tangent negative x will get negative tangent x. And this can also apply to their corresponding reciprocals. So this is because for the cos reason is due to negative angle going clockwise, and this gives a negative angle. But because x, the x-axis is positive, that's why cos is positive. That's why it is positive for cos. So secant is also positive for this reason. Now let's take a look at reference angle. So what it is? First of all, reference angle is denoted by alpha and is in between 0 and half a pi, or in degrees 0 to 90 degrees, and this angle is measured from the x-axis. This is useful to find other angles in each quadrant that give the same value in corresponding trig functions. For example, if you have 1/6 of a pi and the other angle is 5 pi over 6, then if you use the sine function, it give you the same value. So how do you do this is that you refer to the unit circle and compare which trigonometric functions are positive in which quadrant. Like example, if you have angle that is more than 360 more than 270, but if you have a reference angle and cosine the angle is equivalent to that angle found that is like in between 270 to 360, then eventually you that cosine value will be equal. That's because that's how trigonometric function works, and all you need to do is you need to refer to the unit circle and, like I said, compare the trigonometric functions which are positive in which quadrant. Now let's look into some identities like Pythagorean identities and quotient identities. Okay, so notice that I've already put down the Pythagoras theorem. A is adjacent side, O is the opposite, where H is the hypotenuse. And if you take opposite divided by adjacent side, you eventually get tangent. And if you take sine divided by cos, you eventually get a function that is tangent, and this will give you the identity. And to do this, you just need to use the proof that's found in Pythagoras theorem and trigonometric ratios, and like try to combine them. And then for cotangent, you just need to like inverse the operation for tangent. And to get Pythagorean identities, which is on the bottom left corner, just take the squared values divided by the variables found in the Pythagoras theorem, and you eventually get all the three identities. The proof is very simple. However, I put this here as many students they don't know how to get it, and because of this I decided to explain why these identities exist. You need to use them so that these ones can simplify the operations that you encounter later. Now let's look into the addition and double angle formulas. You might want to ask yourself, why can't you just use the one above, like a sine bracket a plus b equal, and then get the value? And why not just try sine a plus sine b and then you get the answer? The truth is, when you try it, they're not going to be equal to each other, regardless of which angle you're going to use. So if you take sine 30 plus 60 and close with a bracket, and in degrees, you get sine 90 degrees, which is equivalent to 1. But if you try separately, like sine 30 degrees plus sine 60 degrees, your answer is going to be different. So this operation is not going to be equal to the other. For this reason, we are going to look into the sum and difference formula. So if you see on the left, the sum and difference formula, you can get it by using the two triangle method, and is combined, so that you can get all the operations that are found in the addition. To get the minus, however, you just need to make the variable b minus b to get it to plus negative b and enclose with the bracket. To get tangent, you just need to take sine divided by cos as explained by the operation from earlier. And to get the double angle formula that you see on the right, just make b equals to a and then you solve it from there. Use the sum formula and you get the result for sine, cosine and tangent. That is all. Now let's look into harmonic form. So what's the use of harmonic form? First of all, is used to simplify trigonometric expressions involving both sine and cosine by condensing into a single form. So if you look at the ones on the right, you can see the harmonic form is right there. So how do you get it? The proof is you use addition formulas to connect harmonic forms with the original expressions. Then afterward, you group corresponding terms and provide formulas for both r and alpha. So r is simply the amplitude of the harmonic function, and alpha is the phase angle. So the harmonic form depends on the original equation. Like example, if your expression starts with a sine, then your harmonic form must start with a sine, and the sine is also as important since you're going to use the addition formula. So if the expression starts with sine and has a positive, then you need to use the harmonic form of sine positive the operation inside the function. If you use cos, then you're gonna have to start with cos. However, inside the argument of cosine, you need to use a negative for the original expression. Since the cosine addition angle, you want to plus the two angles together, you need to make sure that the expression has a negative in it. And so after you find the proof, eventually you get amplitude r equivalent to a squared plus b squared, and phase angle is alpha equals to arctangent b divide a, and r must be more than 0, or to say positive, and alpha must be in between 0 and half a pi. Degrees can be used. Now let's look into inverse trigonometrics. So this is made by reversing the original three functions. Like if your original function is sine, the inverse is sine inverse sine, which is sine power to negative 1. This can also apply to cosine and tangent. But to avoid confusion with reciprocals, we use the term arc instead of power to negative 1. The inverse provides original graphs by reflection of y equals x. And if you look at the diagram on the right, this is an example of graph for arc sine. However, the range of these arcs are limited due to a one-to-one relation, mainly because the sine, cosine, and tangent functions, they are continuous and they are repeating. So to make it look like they can do the reverse, eventually the range is limited to, let's just say, for sine, for arcsine is in between negative half a pi to half a pi. As for arc cos is limited to 0 to pi. So inverse trigonometrics is all you need to realize is that if your original function is sine, like I said earlier, the inverse is arc sine. If it is cos, then the inverse is arc cos. The same will occur with tangent. So original function is tangent, then the inverse is arctangent. And that is how you do inverse trigonometrics. Now, I'd like to conclude my video with just a few facts. So, the reason I made this video is because most AndyMath students struggle in this chapter. Most of them are SPM and IGCSE students, but I also made this for A-level students, as trigonometry is a difficult chapter. As there are some things that are not taught here, such as complementary angles with trigonometry, but I don't think it's so important to put in this video. I want to remind you guys that proving oneself is important, since it helps you understand deeper and takes you further than most students. Some students may still use degrees, which is acceptable. However, in the future, like studying physics and further maths, you're gonna study in radians. And if you want to look into radians, go back to circular measure in my previous video. And this chapter is one of the most liked chapter for me, is because it's such an unimaginable encounter in AndyMath that when the first time when I saw trigonometric identities, it literally blew my mind as to why they really exist in the first place. And it's similar to when I saw about logarithms. I thought it was just magic, but when I proved this myself, like exponential and logarithms and trigonometric identities, I never realized how simple these were. That was when I was studying SPM A maths, and literally that has just it's just crazy. Maybe because one time, the first time you see, you don't believe it until when you prove it yourself. You realize how simple it was to get it. And this is something that I like to share. That is all for me, and this is all for my video. Thank you.